All right, now we'll talk about Chapter 4, Reactions in Aqueous Solution. One of the first parts that we talked about here was the procedure for writing ionic and net ionic equations. And so you'll assign charges to atoms and polyatomic ions in the reactants, and then switch the ionic partners. In general, I find it easiest to leave the cations, which come first, in place and switch out the anions. You'll always pair the first metal with the first metal cation with the second metal anion, and the first metal anion with the second metal cation. Never pair positive with positive or negative with negative. Once you've done that, you'll fix the formulas for the products that you've made, balance the molecular equation, check the solubilities using the solubility rules. To get the complete ionic equation, you'll write aqueous compound as dissociated ions, and then to get the net ionic, remove the spectator ions. And we'll have a specific example here right now. So this is what it'll look like. You would be provided with the two reactants, and those have to both be soluble. And so we have them written as aqueous. And it's best to go ahead and take this part and assign the charges. So you could either know that zinc is always 2 plus, or know that nitrate is always 1 minus, or you can know both, but you need to figure out this is zinc 2 plus, nitrate 1 minus. Sodium's in the first column and it has a +1 charge. So these three sodiums together is +3, and so phosphate is PO4 with a 3 minus charge. Okay, and so on the left-hand side here, just put in charges and then switch the anions. So I left the zinc as first and the sodium as second, just like it is with the reactants, and I switched the anions. But you should notice right away that this first product is not charge balanced. It has a +2 charge and a 3 minus charge, and so we have to do some work to have the charges balanced here. This one's actually okay, plus and minus, so that's a neutral compound. So we need to fix the formulas. And one little trick that you may already know is you can do something that's sort of like cross-multiplying, where the charge of the anion comes down and becomes the subscript of the cation, and the charge of the cation comes down and is the subscript of the anion. However you get to it, this is the formula. Zinc 3, PO4 in parentheses with a 2, and then, like I said, NaNO3 is fine as it is. So now we fix the formulas, but you should notice that things aren't balanced. For example, on the reactant side there's 1 zinc, on the product side there's 3 zincs, and so we need to balance it. Going from here to here is just normal balancing process, and we get 3 to 2 to 1 to 6. After we've worked all this out, we want to see which, or if either of these are insoluble, and nitrate salts are all soluble and sodium salts are all soluble, so this is aqueous definitely. Phosphate salts are usually insoluble. Zinc is not an exception to that, so this will form an insoluble solid. Okay, so it gets marked as a solid, and the other one, which stays in solution, is marked as aqueous. So now we go in, and anything that's aqueous we're going to write as separate ions, making sure to multiply through any coefficients that we need to. So 3 zinc 2 plus, we need to write the charge aqueous. 3 times 2 to give me 6 nitrates. 2 times 3 to give me 6 sodiums, 2 times the phosphate to give me 2 phosphates. This is all stuck together, so this is a solid in the bottom of the flask now, so it's not written as dissociated because it's not. This is sitting as a solid at the bottom of the flask. Now this is all aqueous, so 6 sodiums aqueous, 6 nitrates aqueous. It should be pretty obvious what will cancel and what won't here. So 6 nitrates as a reactant, 6 nitrates as products, cancels and cancels, 6 sodiums as reactant, 6 sodiums as products, and so what's left is the 3 zincs get together with the 2 phosphates to make solid zinc phosphate. Simple bases, we'll just talk about this really fast because they're very easy. You name the cation and then add the word hydroxide. So sodium hydroxide, magnesium hydroxide, barium hydroxide. And the only common base is NH3 only common base that doesn't fit this. This is not a hydroxide base. NH3 is called ammonia. This is a weak base. Common weak base for general chemistry. All right, then concentration units we introduced in this chapter. The amount of solute present in a certain quantity of the solvent. Molarity, number of moles of solute dissolved in 1 liter of solution. And usually this, for us, is an ionic compound, so something like sodium chloride, a solid dissolving into liquid water to make a solution. So salt plus water to give us a saltwater solution. This form is the more useful for us when we're doing calculations. You would be provided something, a number with this big M. You want to expand it right away to this to say that there's however many moles of solute per liters of solution. We'll use this here in a second. So the units can be written as a big M or the more useful mole per liter. Do not use the big M in your calculations. You would only use this to present an answer. You'll want to use moles per liter so that you can cancel units as you need to. All right, and one of the places that we use this right away is dilution. In a dilution, the number of moles of the solute stays the same, but they're distributed over a larger volume. And in this question, we're asked what volume of a 0.100 molar potassium chromate solution must be diluted to make 275 mLs of a 0.0010 molar solution. And we want to find the pieces, so volume, and this is the concentrated volume, okay, because it's the volume associated with the concentrated concentration. Okay, this is the more concentrated, this is more dilute, this is a smaller number. And then down here, this is the dilute volume and the dilute concentration. So as we do a dilution, the concentration drops as the volume increases. And that's how this is equal to each other. The concentration drops proportional to the increase in the volume so that at the end it's a constant. So we just take and put our pieces of our problem in here now, and if we cancel our units, molarity and molarity cancels, and we get a volume unit out, 2.75 milliliters. Therefore, enough water must be added to 2.75 milliliters of a 0.100 molar potassium chromate solution to increase the volume to 275. So the concentration dropped 100 times. And so we take this and we increase the volume 100 times to cause that to happen. A 100-fold increase in volume leads to a 100-fold decrease in concentration. All right, and finally for chapter 4, we want to talk again about titrations, which uses the concept of molarity. A 25 ml sample of a solution is analyzed for its sulfuric acid concentration. It takes 46.8 milliliters of a 0.661 molar sodium hydroxide solution to neutralize the sample. Find the molarity of the acid. So right away, you're given up here just a volume of the sulfuric acid, whereas for the base, you're given a volume and a molarity. So this is something that we can sink our teeth into here in just a second. First, we need a balanced chemical reaction. And so the main important thing to get here is this acid produces 2 H pluses, and so we need 2 OH minuses to react with that acid completely to neutralize it. And so you can write the balanced chemical equation, or you can just write out that 2 NaOHs react with 1 H2SO4. But this is the full balanced chemical equation. Once we have that in hand, and here I've taken the volume and turned it into liters by dividing by 1,000, so 0.0468 liters of the sodium hydroxide solution. The concentration of that sodium hydroxide solution, 0.661 moles of sodium hydroxide are contained in 1 liter of the solution. Now is when we need this mole ratio. Well, it requires 2 moles of sodium hydroxide to neutralize 1 mole of sulfuric acid. And now this calculation, the cleanest way to present this for us is to go ahead and calculate out the moles of the H2SO4. Okay, and those moles of H2SO4 were present in the 25 ml, so we're going to use that now. So the 0.0155 moles of H2SO4 were contained in 25 mLs, or 0.025 liters. put that into a calculator, and we figure out that the concentration of that H2SO4 solution is 0.620 molar.